Sigma X has built an innovative enterprise software stack that breaks the bottlenecks between AI and ML and data. 100 times lower latency, 20 times more data, edge to enterprise to cloud. In this video, we will functionally demonstrate an end-to-end data flow from ingest to message broker to AI and ML. Let's take a closer look at data being produced to a central broker. Millions of producers can concurrently send information to the broker. Millions of consumers retrieve recent data from the broker, and the number of brokers can scale up to thousands. But there's more. By first placing data into Apache Arrow, the brokers become faster and more responsive by orders of magnitude. We'll be showing the Sigma X hardware accelerated high-use schema pathway for ingesting records into Apache Arrow. This pathway stacks latency and throughput benefits on top of the benefits of a CPU-based approach. It is ideal for processing data schemas, which are used often and seldom change. Once our data is in Apache Arrow, it's computable as is, no converting from one format to another, no brittle spaghetti connections, reclaimed power and compute cycles. We'll start the demo by focusing on the data ingest portion of the Sigma X stack, which we will then follow by examining data delivery to AI and ML coming out of Apache Pulsar. On the inbound data path Arrow, IPC messages will be created from JSON sensor data. It will be consumed by an Apache Pulsar broker and produced to a client application which has subscribed to the relevant topic. We first begin by starting up the Apache Pulsar broker, shown on the bottom right. It also spins up a socket for Apache Arrow IPC messages to be produced to. We'll also start up ILX here. ILX needed to be developed by the Sigma X team to generate random JSON sensor data in a predefined schema fast enough to keep up with the hardware accelerator. So this will be our data source in this example. We'll start the consumer host application, which you will see connects with Pulsar. When we kick off Bolsun on the top right, which performs the data conversion to Apache Arrow, what you'll see is 20 JSON records being generated by ILX. The FPGA will transform the data into Apache Arrow and produce the data to an Apache Pulsar topic. The host application is subscribed to this topic. Pulsar produces the data to our application. On the upper right, Bolsun shows us a summary that 20 messages were published. You can also see that they were received by the consumer application. We've performed data ingest, accelerated conversion to Apache Arrow, and consumption of data by Apache Pulsar. Next, we will examine the process of producing the data to enable GPUs to act as stream processors. Two options are available to AI and ML clients. First, Sigma X has developed Pulsar access methods with Apache Arrow awareness. We provide an easy and efficient method to transact with Pulsar and read Arrow data as GPU data frames. Second, we support an Arrow flight server for those potential applications that support flight clients instead of Pulsar clients. Some of these are shown in the upper left corner. For our demo, we will be following both data paths, connecting our Jupyter Notebook via accesses from our Apache flight server and via Python methods to Pulsar. Resuming our demo, let's examine the logs of our Pulsar broker. Here you can see in the topic battery, there is a message with an included schema, and then a second message with type record batch, which is the data. We start the Arrow flight client and stream the data. As you can see, here's the data received by Arrow flight. If we go back to validate, you can see Bolsun produced a voltage value of 50. Let's see if we can follow it through to the flight server. There should be a single 50. And there it is. We will jump over to our notebook and do something with this data using Sigma X GPU methods. We will use a linear regression example here in this notebook, which has access to GPU as well as NVIDIA Rapids. We'll begin by showing the Python module reading and writing directly from Pulsar, and then we will show an Arrow flight example. Before we begin, here's a little more on the setup. What we'll assume is the list of voltages are from discharging batteries, and that their values result from sampling with the uint time interval. The values are random and they will be sorted from high to low. The model we've created generates this data based on a linearly discharging battery. In 100 time steps, the battery goes from fully charged 100% to 0%. When we run the predictions, we will compare the prediction output with this model and when the predicted value is larger or higher, within some error margin, than the last reported voltage level, this may indicate that the battery is discharging faster than it should. In this case, we generate an alert with the unique identifier of those batteries to indicate that someone should go back and check them out or replace them. Let's look at the code. The first step is to generate the model, and we'll do that here. As you can see, the coefficient and the intercept indicating data matches what we described, a discharging battery in 100 times steps. Because the schema is different from the data that we currently have in the battery topic, we'll have to prepare a new data set with unique identifiers and also random voltages that also result in some failing batteries, as we've defined before. So we'll do that here. Generate 100,000 items. Note that this is already in a GPU data frame. Now that we have this data in GPU memory, we will still need to send it to Pulsar. Typically, this would be done elsewhere, but for this demo, we're going to show that Python modules write capability. In this case here, the send method takes care of sending the GPU data frame to Pulsar, publishing it. If we assume the data came from elsewhere, we want to read that data back into a GPU data frame, and this is where we can use the read capability of the module. We're going to read the data back into a GPU data frame so that we can run the predictions on them. We have the GPU data frame back in GPU memory, and we can use the cuML library to run predictions and generate the alerts. This is what the cell does. As you can see, there are a little bit over 2,000 batteries that we can indicate as failing. For example, the first one we predict that the latest voltage level would be 6, but the last one reported is 2. We want to publish these alerts back to Pulsar again so that someone can act on them. We can use the send method again, and to show that indeed work, you can also read the alerts back in, and they are the same. Moving on to the Aeroflight example, this shows how we can get to the data from the battery topic using the Aeroflight server. We first import the required modules. We can use the flight client to connect to the server and create a flight descriptor for the battery topic, and get a ticket so we can start to stream from that topic. We can create the reader by calling the doGet methods. And now we have a reader and we're ready to receive the data. What we'll do is we create a loop, and in every loop we get the next chunk and construct a GPU data frame. Using the QDF library, we can compute the length of the lists and add this as an additional field to the data frame. And then what we'll do is we'll print the resulting data frame for the purpose of the demo. So there's our data, because this runs in the loop and the flight server is streaming. We can run Ilex and Bolsun again to get some more data. And because it will end up in the battery topic, we should see this loop, run the computation again, and the data should show up here. Start Ilex, start Bolsun again, and check what's going on in Bolsun. Also, we are going to run the same parser again. It started parsing, so let's get back to the notebook server. And there are new messages. They stream directly using Aeroflight. And that concludes this demo. Thanks for watching. Trusted by the best in the business. Compute at the edge, faster and with lower latency. Sigma X.